welcome, Mr. Nendick here, and this is a prelection for the longest lab you're going to do this year, which is our soap lab. Specifically, you're going to be making soap for the Rockhurst Soap Co., something we founded in February of 2022. So here we are. We're going to make soap, and it's going to carry the name of Rockhurst. It's not going to carry your name. It's not going to carry like Mr. Nendick's chemistry class. We're going to say Rockhurst made this soap. Now, that's to say you were part of Rockhurst and you made this soap. And the soap isn't just something that we're going to look at and be like, that's a cool thing, let's throw it away. We want them to look and smell good. We want them to certainly work well. And when I go online and I look at bars of handmade soap with the same ingredients that we're using, like on something like Etsy, here are the first two results. They're like $6, $7, $8 a bar. And you're going to make quite a few bars. Your group of 4 or 5 students will make something in the neighborhood of 10 bars. So you're going to make like $70 worth of soap per group. And you're going to get to take home a decent amount of that. And some of it's going to come back to the school and we're going to sell it at the auction. And the idea isn't necessarily to make something quite this elaborate, but we want it to look good. We want it to be something where a person at the auction picks it up and says, yeah, this is worth my money, because we want them to buy it so they can give some money back to the school. And what that money goes to, just to be very clear, is the work grant fund. So the students who couldn't be here necessarily without financial help, they can get a little bit of help from the students of Rockhurst making a product as part of their lab. That's nice. Much more important than that to me, to be very clear, is that you're making something real, something that you can actually touch and use and understand, because like everyone uses soap. Where does it come from? And it's nice to not get a grade just based on a test or a quiz or whatever, but to actually get a grade based on, did I make a good product? Did I make something that someone else would want to use? Though there's a lot of trust being put in a 16-year-old person to do this, right? Like, soap is dangerous, as weird as it sounds, and so we need to make sure we know what we're doing before we go into the lab, because if we go into the lab and we don't know what's going on, we're not going to get a good product. So I'm going to introduce a little bit about how soap is made and the idea and the chemistry behind it, and then I'm going to hand it over to Mr. Doyle, who's going to actually teach you how to make soap. Now, let's be clear. You're going to get more training in this before you actually make the soap. But this is the background knowledge. So here we go. Our first ingredient is going to be olive oil. And by weight, it's like 95% of the soap. Soap is a lot of oil. And we chose olive oil for a few reasons. It's nice. It's a relatively neutral oil. It feels good on your hands when it's made into soap. It's relatively inexpensive, although it's more expensive than some oils. And most importantly, it's very forgiving. You can mess up the soap recipe a little bit and olive oil will still work. Other soaps will not work. And so this is a good first introduction to soap making. So almost all the oil here is olive oil, but unfortunately olive oil is a little bit too soft to actually make a bar of soap by itself. So we're going to add in a second oil called coconut oil, which comes from coconuts. And coconut oil freezes at more or less room temperature. And so it's going to be a solid. And so it's going to help the bars of soap be a little bit more like a bar of soap that you can pick up and use and have feel right. We don't need a lot. It's only like 5%, but we need this. So our oils are olive oil and coconut oil. Importantly, there's no palm oil in here. Most soaps that you buy have palm oil in them. It's because palm oil is cheap. Palm oil works really, really well for making soap. It feels really good. It's like the ideal starting substance. With one little problem. Making palm oil is really not so good for the earth, because palm trees only grow in very specific places, and those places tend to be currently occupied by rainforests. So to make palm oil and make it cheap, basically what you have to do is cut down the rainforests and replace them with plantations. Now, on the one hand, it's trees for trees, so it doesn't seem like such a bad idea. But in reality, you're taking a biodiverse thing like the rainforest and making a plantation, so that's really bad. You're taking away the habitat of things like orangutan and other really important species, right? Obviously, a plantation doesn't have the same climate change potential that like trees do. And so all these things together means this is a really big ecological disaster, let alone landslides and preparations and lots of problems that come with palm oil. And so we really wanted to come up with a recipe that avoids palm oil. So in addition to making a good product, we're also making a product that's a little more sustainable here at Rockhurst. Specifically, it's actually something called a Castile soap. It's so named because the soap you're making is thousands of years old, and it comes from Castile, Spain, this center region of Spain where they grow a lot of olives, which makes sense. We're making an olive oil-based soap. And so we're going to use this kind of centuries-old recipe for soap, minus the coconut oil, that's relatively modern. And you're going to step into this kind of first soap that works well. We also want to decorate the soap with something like a mica powder for color. Maybe you want to put some flower buds in there for some texture. We certainly want to add some oils into it, something called an essential oil or fragrance oil to give it a smell beyond just like olive oil soap. So the scents we chose may change year to year, but the scents we're choosing here for our first run are sandalwood and eucalyptus, milk and honey, lavender. We've got these different smells that should give the soap some different bits of character. So when someone likes how one is, they can choose it, right? These aren't really going to change the chemistry, although I want to point out that the oils can actually make the reaction go way faster. So just know we're not going to add a ton of them. But you might notice, so far we're adding a lot of oils. We've got an essential oil, a coconut oil, an olive oil. So what else goes in soap? And the answer to that is actually a chemical called sodium hydroxide. So we've gone from these like natural things like olives and, I don't know, sandalwood extract. And now we're talking like sodium hydroxide. If you look at these warnings, they're like, whoa, if you eat it, it like breaks you into pieces. It will like eat your skin off. Sodium hydroxide is scary. And I want to be very clear. This is your first warning. We have to take this lab with a lot of respect. Sodium hydroxide will mess you up, especially your eyes. A little later, Mr. Doyle is going to show you just how strong of a base we're using here. But this stuff will burn your skin, and it will be permanent. It will blind you. You have to take the right precautions. Now, I don't want to scare you. We're in a lab. If you get it in your eyes because you are stupid and not wearing goggles, you've got a couple seconds to get to the eye wash station. If you get it on your hands, you can wash your hands off before they're a lifelong burn. But if you just say like, oh, whatever, it's no big deal, it's on my... It will start to burn you. It will make you go blind. So you need to treat this with more respect. This is one of the most dangerous chemicals we're going to use this year. And the concentrations we're using are way stronger than anything else you've used so far. You might wonder, like, how did humans do this in Spain 1,000 years ago? And the answer is they actually used fire. And when you burn, like, wood, it turns to ash. Right? And this ash is white. And the reason why it's white is most of the carbon, the black stuff in this picture, the charcoal, has burned off and turned into carbon dioxide and water and other stuff, right? And the white stuff that's left over, that turns out to be a lot of different chemicals. But one of the most common ones in there is something called a hydroxide. And we know from Arrhenius theory that hydroxides make bases. So if you soak wood ash like this in water, you're going to get a hydroxide solution. And if you soak a lot of ash in water, you get a strong enough solution to turn fats into soap. We're doing the same thing. We're just not using ash, which is dirty and kind of contaminated. We're using the pure good stuff, right? It makes it a lot easier to follow a recipe. But if you really wanted to, you could make soap out of oil and ash, and it would work. Okay, before we get into this, we do need to know a little bit of chemistry we haven't learned before. Carbon is very special because it can bond to 4 things. And like here are 3 different gases you've probably heard of, methane, ethane, and propane. And you might notice that these different gases all change by the number of C's they have. And so when we draw them, most chemists kind of assume that you know that the C's and the H's bond together, because anything that's not a C in what's called an organic molecule is an H, unless we write a different layer in. So instead of drawing it this way, we might draw it like this. And what that means is every time that there's a vertice, every time that the line changes direction, there's a carbon there. And anytime there's nothing drawn there, any open space is a hydrogen. So this thing's got 1, 2, 3, 4, 5 carbons there, right? Each zigzag. The OH group, that's not a carbon because there's something else there. Do you need to know this? No, not really. This is organic chemistry. This is a college level class. What I want you to know is zigzaggy lines mean carbon, right? And this zigzaggy line mixture is something called a triglyceride or a kind of a fatty acid. And there's two different parts to triglycerides. There's this purple tail and this red head. And what those purple tails do is they attach to each other using that red head. This is all over your body as fats. And in oils, this is one of the really common chemicals in there, are these triglycerides, right? So when we're talking about olive oil and coconut oil, we're really talking about stuff that looks like this to a chemist, right? And when we talk about olive oil, actually there's lots of different kinds of them, right? Most of them are like this oleic acid at the bottom, but there's lots of different pieces here that all attach to that front molecule holding it together. You might notice there's some weird places here where the line does weird things, and those are double bonds. It's a carbon bound to a carbon itself, right? And those tend to like kink up the molecules a little bit. They make the molecules a little more likely to be a solid than a liquid. These are the things that kind of make oil a little thicker, or if you add a lot of these things to your fats, they make them a solid instead of a liquid at certain temperatures, right? For right now, I just want you to realize that there's these big, long chains of carbon, right? Because remember, every time that line changes directions, well, that's a new carbon. What we're going to do is we're going to turn it into this. It looks like a big, long, zigzaggy chain. And you're right, it's a big, long, zigzaggy chain. That's what we started with. The only difference is that front, where the OH is, it's going to get attacked, and it's going to turn it into this ionic group. So now it doesn't seem like it, but that whole big long tail, well, that's just kind of like a chloride ion or a nitrite ion, right? It's just an ion that carries a negative charge. But because there's a positive and a negative charge, the soap does something very special. And that is it splits into those things in the water a little bit, and it forms kind of opposite ends on itself. This big, long tail is hydrophobic. Phobic things are afraid, right? So this big, long tail doesn't like water. It's because it's nonpolar. And up front of the head, kind of where there's that ion thing going on, well, water likes ionic stuff. So it's going to be hydrophilic. It's going to attract things in water. And what's special about soap is in the same molecule, you have a hydrophobic area and a hydrophilic area. So any chemical is going to either like water or not like water, be polar or non-polar in one way. It's going to be attracted to one part or the other of this chain, right? What we're going to do is we're going to take these triglycerides, cut their heads off, and leave behind this like ionic long chain piece of a fatty acid salt. Well, a fatty acid salt, another name for that is a soap. The soap isn't going to lose that glycerin you see up top. It's just going to stay inside the soap, and it's going to help it not dry out your skin so much. You might also notice that this reaction here, it says it takes NaOH and heat. The heat is actually going to come from the reaction itself. Once the reaction starts, it's going to warm up the soap, and the reaction will keep going until it uses up all its reactions. So we don't have to like heat this up with a hot plate or a burner. Once you mix the chemicals, this reaction can't be stopped. Really quickly, the reason how soap actually works is you've got that polar and non-polar part, right? That hydrophilic and hydrophobic part. And what will happen is that like non-polar part will grab onto like a germ or bacteria or dirt, right? And it will cling to it. But the head, the polar part, still wants to be in water. And so it gets pulled up into the water. And so the dirt that was stuck to your skin or stuck on your clothes or whatever is now stuck in the water. And if you wash that water away, well, now it's clean, right? So what's going on at a chemical level here is actually pretty complicated. And if you want to know exactly how to make a hydrophobic, hydrophilic soap, well, there's a lot of chemistry that goes on here. But that doesn't really matter because we've already done it all for you. Here's the recipe that every bar of soap that Rockhurst makes will go through. And we know this recipe because we've tried it out lots of times. We've talked with professional soap makers. We've checked it against soaps that you can buy commercially because we really want the product to be safe, right? If you put in the wrong amount of lye of sodium hydroxide and you try to make soap out of it, what's going to happen is your soap is going to look like soap and then it's going to burn people's hands when they use it. If you don't put enough lye in, you're never going to get soap at all. So this ratio and stuff is actually something we've calculated very, very carefully for Rockhurst. And you don't need to memorize it or write it down or anything right now, but it's what you're going to use and we're going to help you go through. Now that's great. We have the idea of how to make soap, and I've probably bored you to death. Mr. Doyle's going to take over, and he's going to start showing you how you actually do this in the lab. So I look forward to seeing you in the lab relatively soon, and let's go learn how to make soap for real instead of just talking about it.
All right, guys, we're going to start by making the lye for the soap. This is going to be very, very concentrated, so we have to be very, very careful with this. This is going to require us to wear goggles. So we need to get 200 milliliters for each group of the base. It needs to be pretty concentrated. We need to dissolve 133 grams of sodium hydroxide into this 200 milliliter volumetric flask. So we're going to start by measuring that out. All right, so we've got all of our hydroxide added to our volumetric flask. You can see it's quite a bit. It's taking up a lot of volume here. We'll have you calculate the pH and concentration of this separately here in a minute, but we're going to dissolve this in it's a 200 milliliter volumetric flask. So we're going to fill that up to our etching on the neck there. This is going to get very hot. Dissolving this much sodium hydroxide in water, this is going to get very hot. We will check the temperature midway through just to see how hot it's getting.
So what we need to do next is actually calculate the pH and molarity of the base we're going to use to make this soap.
So as it turns out, the lye that we need to make for the soap is very concentrated. We need to put 133 grams of sodium hydroxide into 200 milliliters of water. So I'm going to calculate it for you here in a second, but I want to see if you can do it on your own. Find the pH of the lye, and I think you will be surprised by the value that you end up with. So with the information here, go ahead and try to calculate that. I'll do it for you in a second, but we'll see if you can figure out on your own first. Okay, so first we want to find the moles of the sodium hydroxide. So we'll take the 133 grams divided by the molar mass of 40.00. Get 3.32 moles of sodium hydroxide. That's a lot. I see a picture at some point here of just how much that looks like inside of our container. To find the concentration, so this is hydroxide, right? So we're finding the hydroxide ion concentration. We'll divide that by the volume in liters, so divided by 0.2. We get 16.6 molar. This is very concentrated. That should have surprised you when you saw this number. This would be really not good to get on you. If you do at all, you want to rinse this off immediately. This would not be something you want to have stay on you at all. Okay, and definitely not something you want to get in your eyeballs. That would be really bad for them. But if we plug that in right to the pH square, we can find pOH by taking negative log of the hydroxide ion concentration. Well, now it's negative log of 16.6, which is going to be a negative number. I have a negative pOH. It's negative 1.22. And then from there, I can calculate pH, which is 14 minus pOH. 14 minus negative 1.22 is 15.22. Okay, that should raise some alarm bells here, right? This is now outside of our 0 to 14 bounds, right? That means that this thing is so darn concentrated, it's actually outside of the normal range here that we can use to calculate the concentration of something. So this stuff is really nasty, very, very concentrated. Now, that all being said, it is going to be neutralized by all of the acids in the oil and all the olive oil. So even though this is very concentrated and there's a lot here, there won't be any left when it's done.
Okay, so we're going to make soap today. First thing we need to do is to get 950 grams of this olive oil into our glass mixing bowl. So we got a food scale for that. Make sure that you zero it, so tear it with the bowl on there. That should set it to 0, and we need 950 grams. So it should take a little bit less than half of this container. It's going to fill most of our mixing bowl. And it doesn't have to be exactly 950, but you want to be close. If I go over a little bit, that's okay. All right, perfect. 958, we'll call that good. So that's the first thing we need to do. So now with the olive oil, we need to mix in with that. This is coconut oil. Now it's been heated up. Coconut oil at room temperature is a solid, olive oil is obviously liquid. So it's got a slightly higher melting point than the olive oil, which is going to give our soap a little bit more sturdiness, okay, as it begins to harden. So we're going to mix that in. This is pretty warm. It's a little bit warmer than human body temperature. Okay. And we'll mix that around. So we're going to give it a couple of pulses with an immersion blender here. So we're going to want to get this submerged in the oil, and then you kind of want to shake it a little bit. You don't want any air bubbles, okay, underneath the blender. So we're going to give it a couple of stirs, a couple of quick pulses to get that coconut oil mixed in nicely with the olive oil, okay? So the next thing we're going to add is the sodium hydroxide, the lye, okay? This stuff is really, really concentrated. So if you get any on you, you're going to want to rinse it off pretty much immediately. Okay, it's pretty nasty stuff. All right, so we're going to pour that in, and you're going to see very quickly inside of the mixing bowl a reaction start to happen. It's going to start to thicken up. So pour it around. I'm going to set that over here. And we are going to do a couple of quick pulses. You can see just by doing that how it's starting to thicken up. It kind of turns like an olivey milk color. Okay? So after a couple of quick pulses, what you'll want to do is kind of just stir it by hand. You don't want to keep holding a pulse. It's actually bad for the motor, and this stuff is very, very thick. So you only want to pulse it every once in a while to kind of mix the stuff at the bottom. But you want to stir it just kind of by hand, all right, for the most part. It's going to begin to thicken up. You want to do this for a few minutes. You want to get all of that lye, all of that hydroxide reacted. Okay, you want to give it time to react. And then after a couple minutes, we will add in the fragrance, okay, the essential oil, which is going to give it the smell. Today we're going to be adding in oatmeal, milk, and honey. So we're going to add in the fragrance. It's essential oil. This time we're using oatmeal, milk, and honey. You need about 2 ounces of it. It's not an exact science, it's an approximate science. This is a 4-ounce bottle, so we're going to use about half of it. So we're going to pour that in. And these are pretty potent in terms of smell, so you'll notice when you start pouring it, pretty strong odor. All right, that's about half of it. We'll seal that up, set it to the side, and then we will continue stirring. Like I can tell stirring it, it's resisting me moving it around. In fact, it's probably getting close. Not quite yet. Okay, so what we're doing is as we're stirring, we want to look for what's called a trace. So after a couple times of pulsing and after a few minutes of stirring, what we're looking for is as I pull the immersion blender up, you'll notice that you can actually see kind of an outline of where it was, okay? And as some of the liquid starts to fall, you'll see it actually kind of stick to the top. It doesn't immediately go down, okay, like just a pure liquid. So this is starting to solidify to a point where it's called a trace, okay? Being able to see that, it's called a trace.
All right, this is what it should look like for our lab. Just the beginnings of a trace, right? Just those first lines when you lift it up to show you that it's not exactly a liquid anymore. It doesn't need to be super firm, just when you start leaving the very first lines like that, that's when you know it's done and it's ready to pour. It will look like this.
Okay, so the last thing we gotta do is put it into the mold. The mold should be nice and clean. We're gonna pour that in there. Let it be nice and even. It should go right up to the top. And if you got any extra in here, you might take a French spatula. Just try to get as much of it as you can out. It's gonna make your cleanup job with this glass bowl easier as well. So the less of it in here that starts to solidify, the easier the cleaning up process is gonna be for you. Do your best to not get it on the actual outside of the mold or on the wooden container part of it, okay, the box part of it. Try the best to get as much as you can in there. If you get any on the plastic, grab a paper towel and, like I did just right there, grab a paper towel and wipe that off. It is still very basic. You do not want to touch this with your hands unless you have to. You will want to actually just wipe it off and wash your hands if you need to. It's not going to hurt you if you get it on you, but as long as you immediately go and wash your hands. So Once this is complete, we're going to set a cover over it. All right, basically we're just going to take a cardboard cutout, set it over it, and we'll put a rubber band around it and leave it overnight, and we'll check on it the next day.
So to finish this off, let's recap by watching it all in 1 minute. Once your whole area is set up, you're going to measure 950 grams of olive oil and 50 grams of liquid coconut oil and mix them together with the blender briefly. Once they're mixed, you're going to add the lye, which is 200 milliliters of concentrated solution. You saw Mr. Doyle do there. By pulsing, but mainly stirring by hand, you're going to let the lye start to react with the fatty acids in the oil until they start to become more opaque like this. After a couple minutes, it'll be time to add the fragrance oil, what you saw here, and you're going to keep stirring by mainly stirring by hand and every so often pulsing the motor in the blender until you see a trace. That is, when you remove the blender, an outline is left and a drizzle stays on the surface. When it stops acting like a liquid, basically. So this soap is coming to a trace right about now, and Mr. Doyle is going to put that blender aside, and you're going to see him mold the soap. So you pour it into the mold, clean up the bowl with a spatula, and then put a piece of cardboard across the top. That's about it. Now, this hasn't covered really important things like adding colorant, or making 2 different colors, or doing things like adding flower petals to it, or what happens after this. But at least you have an introduction to what's going on in the most basic soap making process. Do I expect you to know everything at the end of this video? Of course not. But I expect you to know the basics. How a soap works. Oh, it's got a hydrophobic and a hydrophilic end. That you need a base, a really, really concentrated base to make it. I want you to know that it comes from normal oils. I want you to know that the process we're looking for involves this trace thing, right? How to use the blender, how to kind of do things in the right order. Because this lab's going to move really fast in your lab. The video you just watched in that 1 minute, that was 14 minutes of lab time for Mr. Doyle. We expect it's going to take you almost the whole period to do this. So there's going to be a lot of things moving fast. So by all means, if you have questions about the process, if you need more clarification, we're going to teach you a little bit more, but don't be afraid to ask us questions because we really want you to have a product that you're proud of and one that you're happy to sell. So thanks for coming into this. We look forward to seeing you in the lab and looking forward to seeing what you make. And for now, en todo, buen camino.